Okay, welcome back everyone. So until now we have seen how to do rectification. We have seen two types of rectifier circuits, a half wave rectifier and a full wave rectifier. So what rectification does is it converts a voltage of two polarities into a voltage of a single polarity. Okay, so if we have a voltage like this, we have a half wave rectifier, then it will convert it will only keep the positive cycles, and if we have a full wave rectifier, it will convert the negative cycles to a positive cycle. Okay, but the aim to do rectification was to convert AC to DC. Okay, so rectification was the first step to convert an AC signal to a DC signal, but as you can see, the output of a rectifier was not a perfect DC signal. Okay, it was a pulsating signal, a pulsating DC. So what we need to do is convert this pulsating signal to a flat signal. So this lecture will be on how we can do that. Okay, so this conversion of the pulsating signal to smooth out these pulses into a flat DC, this is called smoothing. Okay, so this lecture will be on how to smooth the output voltage of a rectifier. Okay, and you would be happy to know that this is actually very simple. Okay, we do not need any complicated circuits or devices to do this. This can be done using only a single device. Okay, and that device is a capacitor. So suppose we have a half wave rectifier circuit. I have a circuit like this. Okay, let me write this at the side first. This was the output of a half wave rectifier, and this was the output of full wave rectifier. Okay, so let me draw the circuit of a half wave rectifier first. I had my sinusoidal signal, I had a single diode, okay, and I had my load resistance. Okay, so what was the output of this circuit? The output of this circuit was like this. So to smooth this pulsating signal, what we will do is we will just connect a capacitor in parallel with the load resistance. Simple as that, nothing too complicated. Just the addition of this capacitor in parallel with the load will smooth out this pulsating output of the rectifier. So how will this smoothing occur? Well, you can see that how does a capacitor work? Well, you might already know that a capacitor stores charges. Okay, a capacitor stores charges, and what a capacitor does is that a capacitor does not allow the voltage between the terminals that the capacitor is connected to change suddenly. Okay, so whenever a voltage starts to rise or starts to fall suddenly, okay, then the capacitor tries to the charge that the capacitor had stored previously, it will try to release that charge to smooth out that voltage, or it will try to store more charge to smooth a rising voltage, and it will try to release the charge to smooth the falling voltage. Okay, so what will this was the output without a capacitor. Okay, this white output was without capacitor, without a capacitor. Now after connecting the capacitor, what will happen is first in the first cycle the capacitor will store the charge. It will rise as before, okay, as it had done if there was no capacitor. Okay, so what is the plot that I'm drawing? This is the plot of the output voltage V out versus time. Okay, this is a waveform graph. As we saw previously, there were 3 types of graphs in our courses. So this is a waveform graph, basically the waveform of the output voltage. So, and the output voltage is between these two terminals. Okay, these two terminals, V out and this is V in. Okay, so what happens after we connect the capacitor? In the first cycle, the voltage, the output voltage rises as before, as if the same way when there was no capacitor. But now when the output voltage starts to drop, you see here that the output voltage is without the capacitor, the output voltage would start to drop suddenly. So what the capacitor does now is that it had stored some charge while the output was rising. Okay, it will store some charge here, and when this output voltage tries to drop suddenly, the capacitor will start to release that charge. Okay, and the voltage cannot drop as suddenly as before. It will drop more slowly. Okay, it will drop like this. It will drop more slowly. Okay, so before the capacitor, without the capacitor, the voltage dropped like this. It had a sharp slope. Okay, it decreased suddenly, and after adding the capacitor, the voltage cannot decrease as suddenly as before. Okay, it will decrease more slowly, and it will decrease in this way more slowly. And if the capacitance value is large enough, then the entire charge of the capacitor cannot discharge fully. Okay, I mean, before discharging fully, suppose the capacitor would discharge completely after reaching, suppose, some large time value. Okay, it takes a large time to discharge completely. But if the capacitance value is large enough, then the next cycle of the output, okay, this was the first cycle and this was the first cycle. Wait, this was the first cycle and this was the second cycle. If the capacitance value is large enough, then before discharging completely, the second cycle of the output will start. And what will happen after the second cycle of the output starts? Well, the capacitor will start charging again. Okay, it will start charging again. Alright, and the same thing that happened in the first cycle will again now happen in the second cycle. You see that the output suddenly decreases at this point. So the capacitor will not allow the output to decrease so suddenly, and the capacitor will start to discharge when the output starts getting down, and it will again discharge more slowly. Okay, so this is the third cycle of the output, and the capacitor again starts to discharge, and before the capacitor can discharge completely, another charging cycle will start. Okay, and this trend will continue until, well, continue always. Okay, as soon as the output is as long as we have output, this charging and discharging cycle will continue. So this blue graph is the graph after we add the capacitor. As you can see, if I just draw the blue part of the graph without the white part, the blue part of the graph will look like this. I'm drawing a zoomed out version. As you can see that before adding the capacitor, our graph was like this. Okay, our graph looked like this. It was very pulsating. Okay, you can see here that this graph was very pulsating, and after adding the capacitor, it has smoothed out a bit. Well, not actually a bit, it has smoothed out a lot. So this phenomenon is called smoothing. Okay, so how fast this capacitor will discharge will depend upon the value of the capacitor. If we select a very large capacitor, then the capacitor will discharge slowly, and if we select a small value of the capacitor, then the capacitor will discharge fast. Okay, suppose we select an even higher capacitor value than the one we drew the blue graph for. Okay, if we select an even higher capacitor, then as before the capacitor will charge. I'm drawing this with the red one, and it will discharge even more slowly. Okay, so the discharging part will be above the blue part. Okay, it will discharge even more slowly, and it will go on like something like this. Okay, and if we select a smaller value of the capacitor, then it will discharge faster. Okay, so I'm drawing this with a yellow line. Okay, if I select a smaller value of the capacitor, then it will discharge faster. I mean, with time the capacitor will lose more charge than before. Okay, so what is better for us? What do we want? Do we want to have a higher value of capacitance, or do we want to have a lower value of capacitance? As we can see that a higher value of higher value of capacitances, our capacitor will discharge more slowly, and for lower value of capacitances, our capacitor will discharge more faster. As you can see that as the slower the capacitor discharges, the flatter our output voltage is. Okay, the more if the capacitor discharges more slowly, then our output will be more flat. If I draw it here like this, for a smaller value of capacitor, suppose our output graph will look like this. All right, it will look like this. The pulses will be more pronounced, and for a larger value of capacitor, our output will look like this. Okay, it will be more flat. Since our aim is to convert AC voltage to DC voltage, and we know that a DC voltage is a completely flat voltage. Okay, so the more flat that our voltage is, the more it will be close to DC. Okay, so the higher the value of capacitance will be, it will be more better for our circuit or for our output voltage, because it will result in a more smoother output voltage. Alright, so this was done for a half wave rectifier. We can similarly do this for a full wave rectifier, just we need to add the capacitor in parallel to the output resistance. Okay, now notice one thing is that after adding the capacitor, we can see that the output voltage is smoother than before, but the output is not completely smooth. There are still high and low parts in our output. Okay, we can see that there is some upper parts and some lower parts. Okay, it is almost similar to waves in water. Okay, like small waves in water. So these small waves that we get on our circuit, these waves are called ripples. Okay, let me write this term. This is called ripple. Okay, so the less ripple that we have in our circuit, the flatter our output voltage will be. Okay, so what we need is a measure of what our ripple will be. Okay, so to do that, first we need to find the frequency of the ripple. By frequency I mean that what is the distance between the upper peak of a ripple and the next upper peak. Okay,